3.1 Derivative of a Function, Part 2. Your objectives for this lesson are to graph the derivative of a function based on the function's graph, to graph a function based on the graph of its derivative, and to find one-sided derivatives. Okay, so when graphing, the important thing to know is that the derivative at a point is its slope. So derivative and slope, same idea. Example 1. Graph the derivative of the function f whose graph is shown. Discuss the behavior of f in terms of the signs and values of f prime. So we're going to start by just taking a look at this graph. This is y equals f of x. You can see the curve here. And we're going to graph y equals f prime of x, or y prime equals f prime of x. So what I'm going to do, I have points A, B, C, D, E, and F. I'm going to find the slope of the function at each point, and the slope is going to correspond to a y value on this graph. So I'll show you what I mean. If I look at point A, I'm going to draw a tangent line here at A to the curve. I have a point at 0, 1, and then it looks like my next point is at 1, I don't know, up here, we'll say 1, 5. So I went up 4 over 1. That means that I have a slope of 4 at x equals 0. So if x equals 0, slope is 4, that is a point over here, 0, 4. Okay, so you keep the x coordinate, and the y coordinate is your slope from the graph of the function. Okay, I'm gonna get rid of this one. Let's look at point B. So I'm going to draw my tangent line. And it looks like B is at about 1, 4-ish. And it looks like my slope is approximately 1. So I'm going to put a point at 1, 1. So this is A prime, B prime. Okay. At C, drawing a tangent line at point C, and you can see this is kind of where the graph is changing. It looks like a maximum value, and the tangent line is completely horizontal. So it has a slope of 0. So this is x equals 2, and slope is 0. Let me put in the one from B quickly. So we had x is 1, and slope we said was 1. So we have a point then at 2, 0. This is C prime. D, we can see the slope here is going to be negative because the curve is sloping downwards. So let's try to draw our tangent line here. This is a little bit harder for me, at least. Okay, so it looks to me, I have a point here at 1, I don't know, 3.5, not 1, sorry, 3, 3.5, and 4, 2.5, maybe, 2. I'm going to call this a -1 for the slope, so D prime. So we said x is 3, and our slope is -1. So because that is a negative slope, you see the y value here is below the x-axis. Okay. For E, still negative. Okay, so this is at 5, I don't know, 1.5. We have a point at 6, maybe 1/2 again. So this one looks like it's still at a -1 down here. So E prime. So X is 5, M is -1. Okay. Last point, F. I'm drawing this tangent line. And that is horizontal also. So that means that we have a point at 6, 0 over here for F prime. Okay. So we see this is a smooth curve. We want to connect our points also with a smooth curve. So let's see if I can do this. The airliner. You can probably do a better job on your paper than I'm about to do up here. So just try your best. Nope, not like that, Walsh. Stuff over here. Okay. So, oh, there we go. That's a little bit better. This should probably curve a little bit more. Other than that, this is a decent graph, really. Okay, and here is the graph of our derivative. So this is a smooth curve, and it's the derivative of the function. It's really a graph showing the slopes of this curve at the different x values. Okay. Now let's look at the behavior, because that was the second part of the example. So I've already written a few things out here. As f is decreasing, so the y values are getting smaller, so that's like from c to f, between c and f, you can see that f prime is negative. So this is when all these values are below the x-axis. When f is increasing, then you might conclude, and you would be correct, that f prime is positive. So you can look back up here, see for this portion it's increasing and we're positive values. Here it's starting to increase again, and this is positive. Okay. When f prime is 0, so talking about this graph, f prime is 0, you see the original graph of f of x has a horizontal tangent line. So f has a horizontal tangent line. There you go. And this would be true. It's not just this is not just true of this graph, this is true of all graphs. Example 2. Sketch the graph of function f that has the following properties. F of 0 equals 0. The graph of f prime, which is the derivative of f, is shown below. I'll show you that in a second. And f is continuous for all x, so that means no holes, no jumps. Okay, so here is our derivative. But let's look at our first criteria first. So we see this is going to be y equals f of x. I know that f of 0 equals 0, so I would point at 0, 0. Okay. And then, let's look here. I can see that starting at 1, I have a slope of -1. So because the derivative has a y value of -1 here, this means my slope is -1 for f of x from 1 and all the way backwards to -infinity. So right here, if I have a slope of -1, that means I have a point here at 1, -1, another point here at -1, 1. So back 1 over 1. We want to line diagonally down. Okay, so this would be our line. Let's make it red. Okay. And then every point onwards from +1 all the way up to infinity, I have a slope of 2. So since y is 2, m equals 2 for f of x. Okay, so that means I'm going to go up 2 over 1, up 2 over 1, and connect these dots. Okay. And this should be a solid dot since we know that f is continuous for all x, and also there are some arrows on the ends of this graph. So this is our original function y equals f of x based off of the graph of its derivative. That wasn't so bad. Okay. Last up, one-sided derivatives. A function y equals f of x is differentiable on a closed interval a comma b if it has a derivative at every interior point on the interval, and if the left and right limits exist at the endpoints. So these limits exist. And you can see for our right-hand derivative at point A, you have the limit as h approaches 0 from the right of f of a plus h minus f of a all over h. For the left-hand derivative at point B, you have the limit as h approaches 0 from the left of f of b plus h minus f of b over h. So it's the same thing, but you have an a and a b, and one's from the right, one's from the left, so plus minus. Okay. Example 3. Show that the following function has left and right-hand derivatives at x equals 0, but no derivative there. So we have a right and a left-hand derivative, but no derivative, no two-sided derivative. So let's start by saying the limit as h approaches 0 from the left, this is our left-hand derivative, of 0 plus h squared. We're using this function because this is where x is less than 0, so this is to the left of 0. If you needed to draw a number line out and see, here is 0 and less than 0 is this way, this is left, this is right. Okay, minus 0 squared all over h. And we can simplify, that goes away. 0 plus h, I know, is simply h squared. So this is the limit of h squared, this is h approaching 0 from the left, over h. Okay, which gives us the limit h approaching 0 from the left of h. And when I evaluate this, when I plug in a 0 for h, I get 0. So my left-hand derivative is 0. Now let's work on the right-hand derivative. So I want the limit of h approaching 0 from the right, and I'm going to use the bottom function this time because this is x greater than 0 is to the right of 0. So I have the limit of h approaching 0 from the right of 2 h plus 0 minus 2 times 0 over h. Okay. And I can simplify this. I know that 2 times 0 is going to go away, and h plus 0 is really just h. So this is the limit of h approaching 0 from the right of 2h over h. And these cancel. So I have the limit h approaching 0 from the right of 2. When I take the limit, I have limit of a constant, which is always itself. So this is a 2. Okay. So I do have a right hand and left hand derivative. So left hand and right hand derivatives exist. Okay, we saw that they were 0 and 2. But they are not the same. Okay, because 0 and 2 are two different numbers. Okay, therefore, so 3 dots in a triangle is therefore, there is no derivative at x equals 0. Okay, and that concludes part 2 of 3.1.